Good morning, students. As I mentioned you in our last class that we have almost come towards the end of the oscillations. Our discussion is going on regarding oscillations and we have almost come towards the end of it. Our today's discussion is we are continuing with oscillations of the loaded spring combination. You must be remembering in our last class I have done it for the initially I have done it for the single spring, then I have done it for the spring combination, parallel combination. Now today our discussion will be regarding the series combination. But before I discuss this series combination, I want to remind you, I want to remind you from our last class, that is, in case of a single spring, the time period of oscillation is m by k. This is for the single spring. When the two springs are in parallel combination, suppose we have seen, then T is equal to twice by root, actually it should be m by kp. P stands for kp, total spring constant of the combination, parallel combination, and that we have seen that comes out to be twice by root m by k1 plus k2. Already these things have been done. In our last class, I just highlight these. Whether the spring combination is in horizontal position or the spring combination is in the vertical position. In both the cases, the formula will be like this. This is for the parallel combination, this is for the single spring. Now, our today's discussion is regarding the series combination. You know, series combination means two springs are connected just one after the another. Just one after the other. Here, there is a rigid support, one spring of spring constant K1, and it is connected to another spring of spring constant K2, and finally the second end of the second spring is holding the mass. It is attached to the mass M. The similar thing is here in case of the vertical position. In the vertical position, this is the first spring, then this is the second spring, and this is the mass. What we do? Either we pull it vertically downward or we make it vertically upward, right? And release. Similarly, either we make it to move towards right or make it to move towards left. Obviously, the frictionless surface, no air resistance, no dissipating force, and we release. We have to prove first that the to and fro motion of this mass about its mean position is SHM. Again, I remind you, all the to and fro motion is not an SHM. For SHM, there should be a condition that acceleration is directly proportional to the displacement and both should be oppositely directed. So many times I have repeated it. Now, what will happen? Whether you pull it downward or upward, whether you pull this towards right or left, what will happen? Some extension will be there, right? In this case, unlike parallel combination, the restoring force, when we leave, the mass will try to come back to the original condition with certain force, that is called the restoring force. In that case, the restoring force in both the springs will be the same. Why? Because when we are pulling it or making it to move up and release, the same force will be transmitted, same restoring force will be transmitted through both the springs. That's why restoring force will be same. In the series combination, I write here, in series combination, restoring force in both the springs is the same. Right? But but the extensions or compressions will not be the same. So we have F is equal to minus K1 Y1 for the first spring and F is equal to minus K2 Y2 for the second spring. That means restoring force will be the same, unlike the parallel combination. In parallel combination, the extension was the same or compression was the same, but the restoring force was not the same. That means what we are getting, Y1 is equal to minus F by K1, Y2 is equal to minus F by K2, then total displacement Y should be Y1 plus Y2, that is equal to minus F by K1 plus minus F by K2, that is equal to minus F 1 by K1 plus 1 by K2. Or we can say Y is equal to minus F K2 plus K1 by K1 into K2. Or we can say F is equal to minus here K1 K2 by K1 plus K2 into Y. And as we know, it is M A is equal to minus K1 into K2 by K1 plus K2 into Y here, which implies A is equal to minus K1 K2 by M times K1 plus K2 into Y. Okay, or we can say K1 K2 M, all these things are constants as M K1 K2 all are constants. So A is directly proportional to minus Y, that means it is SHM. Look, it means the motion of the to and fro motion of the spring is SHM. Okay, then we compare it. We compare above expression. Which expression? This one. With, many times we have mentioned with standard equation of SHM, that is A is equal to minus omega square y, we get. इनको अगर मैं कंपेयर कर दूं तो मुझे क्या मिलेगा? We get omega square is equal to K1 K2 by M K1 plus K2, which implies omega is equal to root K1 K2 by M times here K1 plus K2. Look, that is what is T? T should be equal to twice pi, because considering omega is equal to twice pi by T, we can say M times K1 plus K2 by K1 K2. This should be the expression. Twice pi, here is for the parallel combination, here is for the series combination. Look, this is for the series combination. I just mark it here. Alright, if I now highlight this one, या इसको दोनों में से जो इनके अनुसार क्या होना चाहिए? Now it should be, now in this case T should be equal to twice pi root M, here M by, it should be Ks, where Ks is the total spring constant of the series combination. Here we can say, here I write Here Ks is total spring constant of the series combination. Here Ks is the total spring constant of the series combination. So if we comparing, we get, which are compared? These two expressions are compared. If these two expressions are compared, what we are getting? We are getting here we are getting 1 by Ks is equal to K1 plus K2 by K1 K2, or we can say 1 by Ks is equal to 1 by Ks is equal to 1 by K1 plus 1 by K2. This is also a very important thing. Mind this, series combination, two springs, if they have the spring constants K1 and K2, then their series combination will be given by this formula. Whereas if the two springs are parallel combination, if they are in the parallel combination, for parallel combination, okay, we can get Kp is equal to K1 plus K2. I hope you got. This is Kp is equal to K1 plus K2. These expressions we are getting. Look, very important thing. This is all about the series combination, the expression for the series combination, expression for the parallel combination. All the things are there in front of you on the board. You can very easily observe these things. So this is regarding the series combination and parallel combination of the spring, given spring. Okay, it's all right.